What I want to talk about today is just some examples of derivatives in applied problems. You know, we haven't actually done a lot of sort of real-world examples where the derivative comes up. So I want to try a few, and I want to have like a diverse arrangement of real-world scenarios involving the derivative. The first is a fairly ordinary scenario, and then we're going to talk about some more exotic ones, I guess. The first one is an example that I have mentioned before, and that is in the physics of motion. This is really the principal sort of setting that calculus was originally used for. The physics of moving things. So if and we've done some simple examples like this, but I want to do a little bit more in depth. So if s of t is a function which describes the position of something, with 2 commas there, then the derivative, s prime of t, is also written v of t is the velocity. That would be how fast the thing is moving, because the derivative, remember, it measures the rate of change of something. And if you know what velocity means, it means how fast is the position changing. So v of t is the velocity. This is almost the same as the word speed. Velocity is meant to include direction also. So the velocity could be positive or negative, which refers to moving, forwards or backwards or left, right, depending on the scenario. Okay, and then you could take another derivative here. This would be the second derivative, and that's the acceleration. So this could also be written as v prime. That's the derivative. It's the first derivative of the velocity, or we can write it as a of t, the acceleration. Acceleration, all right? And this also could be positive or negative. So positive acceleration, usually we think of positive acceleration means you're getting faster, and negative acceleration means you're getting slower. That's not exactly true. Positive acceleration means you're accelerating sort of in the forwards direction, which either means you are going forwards and getting faster, or means you're going backwards and slowing down. That would also count as positive acceleration. Negative acceleration would mean accelerating in the negative direction, which would mean speeding up if you're already going in the negative direction, or it would mean slowing down if you're going in the positive direction. This maybe is a little confusing. I'm going to do some details on that point in a moment. All right? Hopefully everybody's clear on the basic setup. This is the standard application of calculus to the real world. Not the only thing, because we're going to do lots more examples. Let's try to do sort of an in-depth example. So let's say we have a particle, I'll say, a thing which is moving according to this function. S of t is, so this describes the position. T cubed minus 6t squared plus 9t. All right? And let's say that this thing is moving from left to right, or it's moving sort of back and forth, left and right. Moving along a line, which has 0 here, and then 1, 2, etc. All right, so the position here, the numbers, like the answer that you get when you plug in a value of t, it tells you its position on this line. So positive motion will be motion to the right. Negative will be to the left, in the way that I'm describing the picture. All right? And you can, by using the derivatives, you can basically answer for me any question you could imagine about describing the motion of this particle. So I want to ask some sort of increasingly complicated questions about this. So here we go. Lots of questions. I got 99 problems about this particle. Not really 99. First of all, let's find a function which describes the velocity. So we're going to start easy here. A function for the velocity. Anyone want to say, how do I do that? Yeah? Yeah, take the derivative, right? S of t is the position, and I already refreshed your memory that the velocity is the derivative. So v of t is the derivative of the original thing. Anyone want to shout it out? Uh-huh. Uh-huh. Great. Yeah, this is a fairly easy derivative. You just do the power rule each time, and there it is. Okay, this is a function for the velocity. All right. How about another specific question? How fast is it moving? Let me say more specifically, how fast and in what direction? Left versus right. Is it moving at time equals 2 seconds? I didn't say before. I mean for the units to be seconds and, let's say, meters for the distances. I'm not, typically in this class, I'm not going to try and confuse you by using weird units all the time. I generally don't care what the units are, but let's say meters and seconds. How fast and in what direction is it moving? Anyone want to suggest how would we answer this question? This also is not a hard question to answer given the setup we've got. What do you think? Plug in to what? The velocity, yeah. The question is how fast. So I should be thinking about the velocity. And at t equals 2 means you just plug in 2. Really what I'm asking for concerns v of 2. You plug in 2. So I get 3 times 2 squared minus 12 times 2 plus 9. I did this in my calculator. You don't really need a calculator. I got negative 3. Can we say, first of all, what's the units for this? Yeah? Yeah, meters per second. This is a velocity, so it better be something, something per, it's a distance per time. So 3 meters per second. So to answer precisely the question which was asked, how fast and in what direction, I would say it's 3 meters per second moving left, right? The speed is the absolute value of the velocity. It's moving left because it's negative there. And I said, just because I said so before, the positive means to the right, negative means to the left. All right? Any thoughts about those? These are, in my opinion, easy questions to ask. All right, here's one that's slightly harder, although still not so difficult. Is it ever at rest? Is there ever a moment when the thing is not moving at all? How would we answer that question? Yes.
Set velocity equal to 0.
Yeah, set the velocity equal to 0. Thank you. We're going to set the velocity equal to 0. And then I guess I'll solve for t. This will tell me at what time. This is more specific than the question I was asking, but this, if I can solve for t, that would tell me at what time the object has velocity 0. All right, so I already have v of t is up here, right? This thing. I'll do a little copy paste here. This is my v of t. I'm going to set that equal to 0, so it'll say 3t squared minus 12t plus 9 equals 0, and then I want to solve that for t. This is a quadratic, so the standard approach would be to factor. You could, I suppose, use the quadratic formula. Rather than directly trying to factor, I'll divide out everything by 3. Since I have a 0 on the right-hand side, you can just divide 3 through the entire equation. It'll say t squared minus 4t plus 3 equals 0. And I think I can factor that. What do you say? What are the factors here? Any factor masters? Yeah. Yeah, t minus 3 and t minus 1. That means my solutions are t equals 3 and t equals 1. So that means it is at rest at those two times. So it is at rest at time 1 second and 3 seconds. All right. Now, if you're thinking about this thing moving, probably this does not mean that it actually comes to a complete halt. Probably this is because it's changing directions, and during the at that moment, at that one instant when it's fully like turning around, it is having no motion at that one moment. All right. Excellent. Okay, how about, I got some more increasingly complicated questions. At which times is it moving to the right versus to the left? This is more complicated. At which times is it moving to the right or to the left? So we'll answer to the right, and then sort of for free, the opposite is what times it's moving to the left. Anybody have a suggestion about this? How could we figure this out? Moving to the right versus the left, yeah.
Put the zeros on a number line, and that's
Okay, I'm actually not going to do it that way. You were suggesting a method. What would you be trying to find by testing the values?
whether it be positive or negative.
Yeah, right. This question has to do with if the v is positive versus negative. Positive v means moving to the right, negative v means moving to the left. So at which times is it moving specifically to the right? This means that v of t is positive, right? So the goal for this one is we have to figure out for which t values is it positive and for which is it negative. There are a few ways to do that, and if you've learned how to do something like this by some other method, then you can do it however you like. He said something about make a number line and plug in test points. You can do that. That's actually not the way I'm going to do it, but that's a perfectly good way to do it. This means v of t is positive. So my question really, like in more mathematical terms, when is v of t greater than 0, right? This is what I want to know. V of t, we already know what it is. It's this formula up here. And in fact, we already know how it factored. So if you'll allow me to factor it out again, this is what we're talking about. Is this thing greater than 0? Because that's the factored version of v of t. When is that thing greater than 0? We can kind of solve for t in an inequality like this, although it's a little inconvenient with the just because of the multiplication in the middle there. But one thing you can do is disregard the 3. Like you can divide through the whole equation by 3, and nothing will change. So this is the same as this. T minus 3, t minus 1 is positive. All right. And we want to keep on working the inequalities, eventually solving for t. When I have two things, their product is positive, it means either each of the two things is positive or they're both negative, right? If these two things, they multiply together and it's positive, it means either they're both positive or they're both negative. So I will say t minus 3 and t minus 1 are either both positive or both negative. All right, so let's just consider both of those cases. What if they're both positive? That means t minus 3 is greater than 0 and t minus 1 is greater than 0. We can solve each of those for t. It says t is greater than 3 and t is greater than 1. All right? So it means this thing is moving to the right whenever t is greater than 3 and t is greater than 1. This is actually kind of redundant to say t is greater than 3 and t is also greater than 1. You don't even need that second part, right? This is redundant in what I'm saying here. So what I can say is, I just say it's not wrong, it's just you don't have to say that. Redo it. I didn't mean to write that. A little redundancy joke. I wrote redundant. The extra done was redundant. Okay, so they're both positive when t is greater than 3. That means the thing is moving to the right when t is greater than 3. What about when they're both negative? That would say t minus 3 less than 0 and also t minus 1 less than 0. You can, again, solve these. T is less than 3 and t is less than 1. Again, one of those is redundant. It's this one this time, right? T less than 1 is the important one in this case. And so I can say, well, what's my conclusion? There are two ways that the velocity can be positive. So v of t is positive. That is, the thing is moving to the right when there are two ways. In the first case, t greater than 3. Or in the second case, when t is less than 1, right? These are the ways in which the velocity, when the velocity can be positive. All right? When is it negative? It's negative all the other times. You could go through all the same steps to derive when the v of t is negative. Would you believe me if I just tell you? V of t is less than 0, I will say otherwise. That is to say, when t is between 1 and 3, right? The first case, apparently it's moving to the right when it's less than 1 or more than 3. It must be moving to the left at the other times, which is to say between 1 and 3. That would be like this. All right? And we already know that it is stationary, that is not moving at all, at time equals 1 and 3, right? So this describes everything about which way it's moving. So it's moving right. If you like, you could write this in terms of intervals. It's moving to the right for t in the interval less than 1 and greater than 3, right? And it's moving to the left for t in the interval in between. The interval 1 to 3. Excellent. Any thoughts about that? Oh, we could actually, I'm trying to get like a very comprehensive view of what this thing does. If you could sort of make a little film, if you will. This thing, it starts here. Apparently it goes to the right until you get to 1 second, and then it turns around and goes left for a bit until you get to 3 seconds, and then it turns around and goes right forever. Right? This is sort of how it works. At time 0, it's over there. At time 1, it starts going back to the left a certain distance. Actually, we haven't said really how far back to the left, but anyway, at time 3, it turns around again and starts going to the right again. Right? This is a summary of what we have determined so far. And then it continues off to the right forever. All right. Questions about all that? Great. I got one more question. Yeah, one more question to ask, which is maybe the most complicated of all of these. At which times is it speeding up versus slowing down? All right. So this is kind of like moving left, right, but it's about speeding up or slowing down. Like I said before, unfortunately, this is not just a matter of telling when the acceleration is positive versus negative. You might feel like acceleration positive means it's speeding up, acceleration negative means it's slowing down, but that's not quite right, because acceleration positive means it's accelerating in the rightwards direction, all right? But that could mean it's speeding up, or could also mean it's slowing down. For instance, when I look at the picture, I would say, I'm going to try to do some blue lines here. It looks to me like it must be speeding up over here, probably. Just because as it continues to go out to the right, I feel like it's going to continue to get faster. And probably even over here. Actually, probably all along here, it's speeding up. After it's stationary right at this point. So in order to move to the right, it must be speeding up, at least soon after this. And then just because the equation continues to go off to the right forever, probably it's going to continue to speed up forever, just because it's a polynomial. Right? Where else is it speeding up? I think it's also speeding up around here. It had just stopped, and it will begin to speed up as it turns around and goes to the left here. All right. So this is speeding up also in this region here. Even though you can tell, like right here, the acceleration will be negative though, because it's actually its speed is increasing in the leftwards direction, whereas the acceleration on this top branch here will be positive. So what I'm trying to say is, it's not just a matter of testing when the acceleration is positive versus negative. It has to do with, is it accelerating in the same direction that it's traveling, right? That means that it's speeding up when it accelerates in the same direction of travel. So what we really have to answer here is, when is the acceleration direction the same as the velocity direction? That means speeding up, right? When the acceleration direction is the same as the velocity direction. If it's moving to the right and also accelerating to the right, that means it's speeding up. Or if it's moving to the left and also accelerating to the left, that means it's speeding up. So this means speeding up. And when those two directions are opposite, that means it's slowing down. If it's moving one way but accelerating in the reverse way, it means it's slowing down. All right. This is a little tricky to figure out exactly when this happens. When is the acceleration direction the same as the velocity direction? There are two options. One is when they are both positive, and one is when they are both negative. So it shouldn't be so hard once we break it down like this. We could have velocity and acceleration both positive, or the velocity and the acceleration both negative. And then we'll just have to consider each of those two cases separately. And we've already been able to say when the velocity is positive versus negative. We will want to, as a preliminary thing, figure out when is the acceleration positive versus negative. And then it shouldn't be too hard to kind of put it all together, right? We decide when is the velocity and the acceleration both positive or both negative. All right, it's a little complicated. Let's see what we think. So first of all, as a sort of preliminary to answering this question, let's say when the acceleration is positive versus negative. This is actually easier than for the velocity, but first we should find a formula for the acceleration. The acceleration, of course, is the derivative of the velocity. I will refresh our memory. The velocity formula was, if I even remember, 3t squared minus, is that right? Sorry, I've forgotten. 3t squared minus 12t plus 9. We had a version of this that was factored, but because I want to take the derivative again, it's better to use it this way around rather than the factored one. Can someone say what's the acceleration going to be then? Want to shout it out? Yeah. 6t minus 12. Great. All right. Is that right? Did I mess something up? Sorry. No, that's right. I have it wrong on my paper. 16 minus 12. I agree. I wrote 9t minus 12 on my paper for some reason. I'm sure you're fascinated by that fact. So where is the acceleration positive versus negative? All right, that's easy enough to decide. A of t is positive when 6t minus 12 is positive, and we can solve this for t, right? Add the 12 over there. It says 6t greater than 12, t greater than 2. All right, so the acceleration is positive when t is greater than 2, and I guess the acceleration will be negative when t is less than 2. All right, so A is positive when t greater than 2, and it's negative when t less than 2. All right, I think we have all the information then to answer this question about when is it speeding up versus slowing down. So let's talk about speeding up. Remember, speeding up means that acceleration and velocity both positive or both negative. right? And we have already written down when all of these things are positive versus negative, so we should be able to just sort of put together everything we've said before. So, when is the acceleration and the velocity both positive? This is one possible situation. A is positive, I just said, when t greater than 2, and v is positive when, I have to look back when we wrote this down somewhere. V is positive when, here, t is greater than 3, I have it right here, t is greater than 3 or t is less than 1. So, t greater than 3 or t less than 1. All right? Can we sort of summarize this? Some of this is redundant or something. So A and V are both positive when, can anyone say more simply? I mean, according to what I said, it's when t is greater than 2 and t is greater than 3 or t is less than 1. What would that all be if we combine it all into a single thing? Greater than 2 and greater than 3 or less than 1. Anyone capable of, yeah? 3, yeah, he says 3 to infinity. I think in order to satisfy all of those, it just has to be greater than 3, right? It's greater than 2 and it's also greater than 3 or less than 1. Well, if it's greater than 2, it can't be less than 1. And so it has to be greater than 2 and also greater than 3. So this means, I will say, i.e., t is greater than 3, all right? As an interval, you could say t is in the interval 3 to infinity, like we said, all right? These are the times when it is speeding up, and in fact, this is when it's speeding up to the right. All right. This is actually on the on our picture. If you don't mind me scrolling for a moment. That's what I said before. This business, right? All the times after 3, it's speeding up, going to the right. That's all those times. Okay, let's just finish. I know we're sick of this problem. What about the other time that it's speeding up is when these things are both negative. So that was one option for when it's speeding up. The other option, this would be when it's speeding up to the left, would be when A and B are both negative. And what would that look like? So again, we're just going to assemble together some information we already have. A is negative when t is less than 2, and V is negative. Sorry. V is negative when t is between 1 and 3. All right, and so both are negative when both of those are true. When t is less than 2 and t is between 1 and 3. I.e., can I simplify that into an easily something more simple than that? What do you think? T is less than 2 and also between 1 and 3? Yeah? Yeah, between 1 and 2, right? It has to be between 1 and 3, but additionally it has to be less than 2, so it better be between 1 and 2. Thanks. All right. T is between 1 and 2. If you like to write as an interval, t is in the interval, 1 to 2, right? And this also I had indicated on the picture, right? You can see this is from time 1 to 2 on this picture. It would be right here. Just after time 1, it starts to speed up to the left. And I wasn't sure, just because I was drawing informally, exactly how far over it goes. It actually would stop somewhere like right around the middle is when it stops speeding up. And then it has to start slowing down and eventually to come to a rest again. All right? These are the times when it's speeding up. That's a complicated question, I think, but let me just write my whole answer. So it's speeding up for, as intervals, t in the interval 1 to 2 and 3 to infinity. And it's slowing down at all other times. So slowing down for t in the intervals, let's just, assuming that we start at time 0, it would be 0 to 1 and 2 to 3, right? Those are the other times. And of course, I'm using all open intervals here. If you want to know what exactly happens exactly at time 1, well, that's a time at which the thing is not accelerating at all. And exactly at time 2 and exactly at time 3, apparently the thing is also not accelerating at all at those times. All right? Or it's not speeding up or slowing down. Actually, it is accelerating and slowing down. That's different from speeding up, slowing down. All right. Are you thoroughly bored with this example by now? This is the end of this example. I'm just trying to demonstrate how using these, fairly simple derivatives plus a lot of other kinds of simple algebra, you can pretty much answer any question you could imagine about this physical system, all right, by using the appropriate derivatives. Any further thoughts about that one? Great. Let's talk about something a little more exotic. So I would like to do 2 or 3, just 2, I think. 2 more examples. Using the derivative, but having nothing to do with speeds or accelerations, and in fact, not even having anything to do with time. Usually when people explain what the derivative means, they say something like how fast something is changing, which implies changing over time. But actually the derivative is useful even in other situations which have nothing to do with changing over time. So I got 2 more examples using the derivative in sort of non-time, without time. All right. So here is one. These 2 examples are going to look completely unlike what I just talked about. Let's talk about a non-homogeneous. This is a favorite example of the author of our textbook. A non-homogeneous rod. You ready for this? This is you imagine like a bar of metal or something. Let's pretend it's a cylinder, although that's not going to matter at all. Non-homogeneous means it's made of some stuff that is not uniform across the whole bar. So if you were to pick up the bar, maybe it would be heavier on one side or the other side. All right, that's what I mean by non-homogeneous. So the weight, or the, let's just say mass, is not evenly distributed. Maybe it's hollow in some portions of it, or it's made of different materials which are heavier on one side or whatever. The mass is not evenly distributed. It's lopsided somehow, even though it's not shaped any differently. It's just somehow heavier in parts and less heavy in other parts. All right? How could we describe such a rod if I ask you, okay, exactly, if it's unevenly distributed, then how can you be specific about how is the weight distributed? If not evenly, how exactly is the weight distributed? You could say something informally like, well, maybe it's heavier on the left or heavier on the right. But if you wanted to really describe this very specifically, I think the only way to describe this, so to describe the mass, you basically have to describe a function that tells you, as I move across the rod, how is the mass changing as I go down the length of the rod. All right. So to describe the mass, you have a function, and we're going to call it m of x. And m of x means the total mass up to position x. And I'll draw a little picture. what I mean by this. The total mass up to position X. So this rod here, oops, which I'm drawing again as if it were a cylinder. As you move down the rod, the mass sort of changes in unpredictable ways, but you can describe that using a function where if I go down, say, this far, and I just chop off like that piece of the rod, m of x is the mass of this piece. Right? That's the function that I'm trying to describe here. And as you move the x across, I suppose this function will always be increasing if you were to look at the graph of such a function. You know, when x is all the way on the left, you have basically 0. And as x moves to the right, the mass continues to increase. It's just a matter of at what points is it increasing more. At some places, it's increasing more than others, right? So this is how you would describe such a situation. For example, what might this function look like? So if the rod is, say, heavier on the left, this would look like, if I were graphing the function, it would look like, you know, when you start on the left, you see like almost all of the weight occurs towards the left, and then as you continue to move to the right, you don't really add on much mass after that. So it would look something like this. That is to say, as you're to the left side of the rod is where you see all the mass increase, and then after a while, there's not much increase at all past a certain point. All right. This is what the shape of the graph would look like for a rod which is heavier on the left side, versus heavier on the right side would be like this. Not much going on until you get like to the end, and then all the weight is on the right end. That's what it would look like if it was heavier on the right side. Heavier on the right. All right. Or heavy in the middle. You think for a moment, what do you think the graph of that would look like if it's heavier in the middle but not on the two sides? You may be tempted to say this, like that. It's actually not that. Anybody have another idea? It can't be this. If you think about it, what you're saying here is, as I start off, there's not much mass. Then when I get to the middle, the mass goes out quite high. And then as I get to the end of the rod, the mass goes back down to nothing. But that's not how this works, right? The function tells you what the mass of this much is. It can only increase as you go across the rod. It can't go back down to nothing, right? Really, if you want heavier in the middle, it means, anyone have another idea? Can you describe the, yeah, what do you think? Yeah, right. It's kind of like at the beginning you don't see any action, just like the heavier on the right picture. Then somewhere in the middle is where all the action happens. The mass goes up, and then after that, it doesn't really increase much more than that. So it's really something like that. This is when all the increase in mass happens in the middle. All right. It doesn't make any sense for this curve to go back down because we're talking about the total mass of the rod. It's always going to end up the same place up here. Just a matter of what it looks like in the middle. Okay, so this, yeah, let me label this. This is heavy in the middle. All right, heavy in the middle. Okay, anyway, this is the, I hope everybody's clear on what we're talking about here. I would like to talk about the derivative of this function and what does it mean in this context. Actually, the derivative of this function has a meaning. What is m prime of x? You know, not what is it as an equation, but really what I want to ask is, what is the meaning of this? Can I say that? What is the meaning in this particular scenario? What is the meaning of m prime of x? All right. in general, if anyone asks me what is the meaning of the derivative, I always say it's the rate of change of something. But in this case, it's not a rate of change over time. It's how fast is the m function changing in terms of the x. There's actually an ordinary word for that in this particular scenario, which let's see if we can think this through. M prime of x is like, I'm going to use that sort of other form of the definition of the derivative just to help us think about this. Remember, this was like the first format of the definition of the derivative. We're not actually going to do the limit of anything because I didn't describe an equation. I didn't give you a specific equation, but this is where the derivative comes from. It comes from looking like at a fraction like that where the b and the a are very close together. All right. What would this mean in the context of this problem? Whoa, sorry. Well, I think this would, just to draw a picture which has some b's and a's on it, you have to imagine you're looking at a little chunk of this rod which is sort of broken off from one point A to some other point B, all right? And what the bottom of this fraction would be, this is the width of the piece meaning, you know, this piece right there, right? And what does the numerator of this fraction represent? M of b minus m of a. M of whatever, remember, means the mass of the whole rod up to a certain point. Anyone say in simple words what m of b minus m of a would mean in this case? It's the mass of the whole rod up to b minus the mass of the rod up to a. Aren't you guys into non-homogeneous rods? Actually, this little pencil I use is somehow non-homogeneous. The weight is not really evenly distributed because I think there's like most of the inside of this I think is a battery, but not quite all of it because it makes it slightly heavier on one side. Anyone still with me? What does m of b minus m of a represent in this case? The m of b would represent the weight of the whole thing from the left end up to b, and the m of a would represent the weight of the whole thing up to a. Yeah. It's the weight of that section between a and b, right? If I take the whole weight from the left all the way up to b, and then I subtract off the weight from the left all the way up to a, what remains is the weight of just this little bitty piece from a to b. So what I have here is the, I guess it's, did I say weight? I mean to be saying mass every time, it doesn't matter. Mass of, really that's the mass of that piece, right? This piece here, between a and b. So this fraction here represents the mass of that piece divided by the width of that piece. And what is that? There's a simple word for this. It's how heavy it is divided by how big it is, right? That piece. This is also known as the density of that piece. It's mass divided by, now usually we use volume for the density, but I don't care about the cylindrical volume per se. It's just the mass per distance of that thing. So this fraction here, in this example, m prime of x is the density, I'll say linear density, like density per horizontal distance, rather than, density usually means per like volume measurement, but I don't care about the volume in this problem. The linear density of the rod at various points. That's what this function represents. So like m prime of 2, it means the density of the material right at distance 2 away from the left end. All right? Which obviously is a useful thing if you really cared about non-homogeneous rods. You would want to be able to know about the density of it at different points. And this is how you would do it, the derivative. All right? This, I said I had 2 more examples. This was the first of my 2 examples about weird scenarios in which the derivative is still useful, and it means something like this on the surface doesn't seem to resemble the ordinary kind of rate of change of something. But the derivative in this case is the density of the rod at various points. All right? This was the first of my examples of a non-standard use of the derivative. Any thoughts about that one? All right, let's. I got one more, and that'll do us for today. How about here is an example from economics or business. I don't know which one this is. Right? You probably heard that calculus is also useful in business economics type scenarios. Let's say this is loosely based on a true story. I'm making jars of maple syrup. I have a big maple tree in my backyard, and I make maple syrup from it in the wintertime. It's a fun and wholesome hobby, which probably, I'd probably lose money on the deal. Probably it costs me more to make it than it would if I bought it in the store, although real maple syrup is kind of expensive. I will tell you my recipe. This is actually every recipe for maple syrup is you get the sap out of the tree and then you boil it, and that's it. You don't add anything to it or anything. You just boil it to remove the water, and you boil it and reduce its volume by I believe it's a factor of 40 to 1. You got to boil it like for many hours. And that's how you make it. So the cost of making maple syrup is basically all in the fuel that you use to boil it. And I've never tried to calculate how much it costs me to make these things, but I'm not sure that I'm really breaking even. But it's a fun thing to do with the kids. Anyway, let's say my costs are given by some kind of formula, C of x, and this is the cost to make x jars. All right? I really don't get a lot of maple syrup because I'm just using the one tree. But let's say C of x is the cost to make x jars of the maple syrup. And my expenses would be the fuel. I actually do this on my grill, on my gas grill outside. Plus, I guess I have to get the jars themselves. Those are my only expenses. So, in a very simple example, you could say something like, maybe it costs me 75 cents to make each jar. All right, they're small jars that I end up with. So, in a very simple case, if it costs 75 cents per jar, then the function would be C of x equals 0.75x, right? X is the number of jars I'm making. In a very simple scenario where it just costs some amount per jar, then that would be the function, 0.75x, all right? But a more realistic scenario is more complicated than that. So usually when you are making stuff, it's not such a simple scenario. Of course, the graph of that would just look something like a line like this, right? With slope 0.75 going through the origin. That's what 0.75x looks like. Oh, I should draw that. I always draw a graph with a red line. I don't know why. Can you even tell the difference? On some of the screens you can. More realistically, though, in a real business, it's not just a matter of each of the things I'm making cost me a certain amount per thing. There is some of that, but there's also like I have to buy the equipment to make whatever I'm making, or I have to pay my employees. The cost is not always directly related to how many of the things you're making in such a simple way. So maybe I will say more realistically, it might look something like maybe like this. Rather than starting at the origin, it might start, say, up here and do something like that, where it kind of asymptotically approaches that same line. But I have extra cost to start up. And in a business, this is called like startup cost or something. Like you have to get all the stuff that you need before you even make anything. In a sense, this looks a little strange because it would say the cost, even if I make 0 things, the cost is still up here. But this is how the world works in a real business. You got to spend a whole lot of money before you even make anything. So a more realistic scenario would look something like that. Anyway, I want to talk about what does the derivative mean in a scenario like this. All right? Again, there is nothing about time in this setup. The function is just c of x, where the c of x is the cost to make x jars. Okay, so I'm not talking about how something is changing over time. It's more like, well, what is it like? So my question is, what does c prime of x represent? It's how much the cost changes when I change the x a little bit. That's the basic idea. It's the rate of change of the cost according to the x value rather than according to time. I want to try and maybe get a little more specific about that. C prime of x is like, in this case, actually, for this example, it's more convenient to use the other format of the definition of the derivative with the plus h in it. Can we try to interpret the meaning of this thing? So, c of x plus h versus c of x, I'm just going to write down what those mean. C of x, of course, is the cost of just x of them. C of x plus h is the cost of making x plus h of them. And you're dividing everything by h. So my interpretation of the numerator here would be something like, if I decide to make extra stuff, if I'm already making some amount of things and I decide to make h more of them, if I decide to make some more things, the numerator here is the cost, I will say the additional cost to make h more, in this setting, jars, right? If I am already making a certain amount, but I just decide to make h more of them, the numerator will represent the additional cost to make h more jars, and then of course I have divided by h. So really what we're talking about here is kind of the extra cost per jar if you decide to make more jars. That's what this fraction represents. I say cost per jar because you're dividing by h. So if I make h more jars, but then I divide by h, it'll be the extra cost per jar. So the meaning of this here, c prime of x represents the extra cost per jar to make additional jars. And this is when we're already making x jars. So the idea is I'm already making a certain amount. What if I decide to make a little bit more? How much is it going to cost per jar? So this is the extra cost per jar to make additional jars when we already made x. All right. I'm already making a certain amount. I want to know how much will it cost me to make a little bit more. How much per jar will it cost me to make a little bit more? Any masters of business or economics know there's actually a sort of a businessy type term for this? There's a word for this. They have some lingo for this. Anybody heard of this before? This is called the marginal cost. It means if I'm already making a certain amount, how much will it cost me to make just a little bit more? In this case of jars, it would mean like 1 jar more. Or in other cases, it might mean just a little bit more, all right? And this actually is extremely useful in a real business. If you imagine a business which already exists, is always trying to decide how much of this stuff should I be making, because they want to create enough supply to meet the demand. Should I make a little bit more? Should I make a little bit less? This is a constant question that you have to ask yourself over and over again. And the marginal cost is one of the basic ways in which you can answer this question. If I do make a little bit more, this is how much it's going to cost me. If I make a little bit less, this is how much it's going to cost me. That's why the marginal cost is important. Let's try just a very specific example with a real equation in there. So, for example, very specific example. Let's say my jars cost, according to this formula, C of x equals 2 plus 3x squared over 4x plus 100. This is a made-up formula, but I tried to make it up, so I didn't just design this entirely at random. I made it up in this way. If you look at the graph of this, it does have this kind of slanted asymptote at the 75 cents per jar level, but the function, you can graph this if you care, looks something like that. So overall, it looks vaguely like a parabola type shape, but it's not a great curve here. Sorry, I'm trying to do it a little better. It does something like that. And on the other side, it looks like that, but the other side doesn't mean anything in this problem. Okay. Let's say this is the price of my jars. And can we just, I'm going to use my calculator to work the numbers a little bit on this, but let's find and interpret the marginal cost at various different levels. So first of all, in order to calculate the marginal cost, we're going to have to find C prime of x. Anyone want to suggest, how would I find the derivative of that? I care about the derivative because it represents the marginal cost. What's my basic approach to taking the derivative here? Anyone remember? This could have been on the test. Take the derivative of that function. What do you think? Is it too late in the day for this? I'll be taking derivatives all night long. Yeah, okay. Yeah, I would say the 2 goes away because it's a constant, and then I'm going to use the quotient rule on the other part because it's a fraction. Thank you for saying that. I know there's some quotient rule haters out there, and that's fine too. You could rewrite that as a product with the -1 power if you want, but I'm going to use the quotient rule. So I go, the 2 disappears, I do the quotient rule. It's the bottom, like so, times the derivative of the top is 6x, and then minus the top, 3x squared times the derivative of the bottom is 4. All of this over the bottom squared. Now, ordinarily, I wouldn't try to really simplify this, but just because I'm about to do some specific plugging in of numbers, let's just simplify it a little bit. I would distribute on the top 4x plus 100 distributes on the 6x. That gives me 24x squared plus 600x. And then I have minus 12x squared. I'm not going to bother multiplying that out on the bottom. This is going to be, the x squareds will combine. I get 12x squared plus 600x over this denominator. 4x plus 100 squared. And I'll leave it at that. All right, that's as simple as I want it to be. Just trying to make it easy to plug numbers in using my calculator. Okay? So let's see if we can find the marginal cost. So let's find the marginal cost at x equals 1, 10, and 100, and see if the amounts make some kind of sense. All right. At x equals 1, remember what this means is if I'm making only one jar and I decide to make one more, how much more per jar is that going to cost me? You could think for a moment. Do you expect this value to be a lot or a little? I don't know. Let's just see what it is. C prime of 1, all right? I'm plugging into this formula up here. using x equals 1. What will it be? I did this on my calculator, but it's 12 plus 600 up top, and then 4 plus 100 squared on the bottom. I did that on my calculator, and I got 0.056, all right? I don't know if this seems reasonable to you, but it means if I am making only one jar, but instead I decide to make 2 jars, how much more will it cost me for the second jar? Only 5 cents to make that second jar, all right? I don't know how realistic this is in my real life, but according to this curve, it makes some kind of sense to me. If you're already making one, you're like here. To make just one more, your cost is only gonna go up a little bit, right? To move from 1 and make 2 instead, all right? Versus, I expect this value to be bigger down here. If I'm making some amount and I try to make a little bit more, the cost is going to be increasing more at that point, all right? Another way of thinking this through is when you're only making one, you're really still very close to the startup cost range. And so if you're only making one, basically all of your costs up to that point have been the startup costs. And if you decide to make 2 instead of 1, it's really not a lot more because the cost has been almost all startup stuff at that point. All right, let's try C prime of 10. 10 is further away from the startup point, so I expect actually, say, to make the 11th jar is gonna be a higher marginal cost than that first example. Anyway, if I do these numbers, remember I'm plugging into that thing up there in the circle, I get 12 times 10 squared plus 600 times 10 over 4 times 10 plus 100 squared. This I did on my calculator and I got 0.36. So that means if I'm making 10 jars and I decide to make more, the next one will cost me 36 cents per jar. All right? It's more this time because now I'm further away from the startup costs. They are having less of an impact on the cost per jar at this point. And I said also, let's try 100. So if I try 100, I get, this same business, but with hundreds instead of tens. I plug that into my calculator. I got 72 cents, all right? Now I'm much closer to the sort of actual materials cost per jar, which I said was around 75 cents per jar, all right? Trying to make this more realistic. So if you're in the business and your question is like, should I make more? I would say at this level, at this point, you should definitely make more because they're only going to cost you 5 cents more each. As you keep on making more and more and more, eventually you get to a point where it's probably not worth it to make more anymore because these are costing quite a bit. All right, this is the end of my third and final example. And I think that'll do it for us today, if you don't mind. We'll talk about something different next time. And maybe I will grade the test tonight, but probably not. Sorry.